Okay, good afternoon. Is this working? Yeah. Okay. Yeah, thanks for inviting me to present at this program today. It's an interesting subject. It's the focus of some of the work that we are developing in collaboration with MDRU as well as with geological engineering, where we've created something called the International Caving Research Network, ICARN. And what I'm going to show you is really a presentation about sensor-based sorting in the context of block cave mining. Sensor-based sorting is a relatively new technology. There has been sensor-based sorting used a long time ago, but it's evolved significantly in recent years. And it's the application of sensor-based sorting today and in the context of block cave mining that is evolving. So I want to acknowledge the different organizations that helped support us to be able to do this type of work, particularly New Gold and the New Afton mine. Stefan acknowledged them as well. They're extremely helpful to us. They basically opened up all of their data, which allowed us to do some interesting analyses, which is not always the case when working with a mining operation. And then there was a number of other organizations that supported us in different ways: MineSense Technologies, Scantech, ALS Metallurgy, Motion Metrics, and Steiner. And of course, we applied for an NSERC CRD grant to support the work, so I acknowledge NSERC. And these are some of the people who contributed, particularly to the sensor-based sorting work. So we're all here because of copper, and recognizing that copper is the demand for copper is going to increase in the future, likely for a number of reasons. One is that as developing economies evolve, they start to electrify. Secondly, we're all thinking about electric cars these days. And at the same time, there is a trend of finding deposits with lower grade and finding deposits that are located at depth. And so we need to find a way to try to mine those deposits at low operating costs. So there's a demand for technology and innovation that is part of this ICARN program that we're working on in order to try to find ways to more cost effectively mine these deep, low-grade deposits. So, despite significant investment in exploration for copper, we're not finding the deposits as easily as we did a decade ago. So some key messages. As Eric pointed out, caving is a risky business full of surprises, and as we go deeper, it's going to become more complicated. It's not suited for marginal projects. There's a need to improve the margins by a reliable cave-to-mill production, and that's potentially by applying this technology called bulk sorting or bulk sensor-based sorting to increase the grade of the material or to separate the grade mined from the grade going to the processing plant. So, as Stefan pointed out, we need better knowledge of the ore body. We need to be able to measure the things that are important, and there's a need for this improved or new technologies and innovation. So we conceived this ICARN, International Caving Research Network, and you can see some of the key people who are involved with this, and you can see that they have different disciplines. So the concept of mine to mill was developed over 30 years ago when it looked at the interface between the mine and the processing plant, and where they realized that by putting more explosives into the ground, they could break the rock smaller, and that had a big impact on the comminution process, increasing production often by more than 20%. So we are stepping back and saying, well, what does it mean for a block cave mine? Stefan focused on fragmentation opportunities, and I'm going to focus on the grade control opportunities. So I'm a process engineer, and as a process engineer, we talk about pre-concentration. upgrading the material and throwing away waste. But when I'm talking to mining engineers, I talk about grade control, a way to improve the quality of the material that's going to the process plant. But technically, they're the same thing. And we recognize that within ICARN, we need a strategy for innovation. So with the for innovation strategy in the center, how does industry, academics, different people, and all play a role? And in addition, how does perception and attitude play a role? My experience is that geologists are optimists, mining engineers are pessimists, and so I've had a lot of experience working with geologists before I joined UBC, and they're always trying to find something new, but as soon as you try to turn it into mine, someone tells you why you can't do it. And so these perceptions are actually really critical, particularly when you're introducing new technology. For instance, I'm going to show you what sensor-based sorting can do on a very large scale in an open pit mine with 75-ton shovels. When I speak to mining engineers, they say, well, copper porphyries are homogeneous. There's no opportunity to take advantages of differences in the properties of the material. Well, that's what the perception is amongst some mining engineers, but the reality is they're extremely heterogeneous, and we can take advantage of that. So the concept here is to look at where we could put sensors in the entire material handling system of a mine. We have borehole sensors that track information along depth, and often the information that the geologists will collect in borehole sensing may not necessarily be transferred to the processing guys. It's used for geological purposes, it's valuable for interpreting the deposit, but those same sensors we may be able to put into the material handling equipment if they're noticing something that's distinctly different between two different materials. So we can put them into shovels, we can put them onto conveyor belts, we can put them into particle sorting systems. We can even use them to classify waste materials, such as acid generating versus non-acid generating waste. So I've been working on this for quite a while. My own PhD started off in pre-concentration technology, which led me into this technology with sensors. And as you evolve a technology and you see a technology evolve, you recognize that there are no systematic approaches to try to assess the potential for such a technology for the mining industry. And so one of the things that we have tried to do is develop a framework for saying, well, how do I know that sensor-based sorting is going to work or going to have a meaningful impact on my project, on my deposit? The first thing is to characterize the heterogeneity. And if you don't have heterogeneity or variations, let's say in grade, then there's nothing to exploit. But if you do have heterogeneity, then how do you classify that heterogeneity? Not only do you see fluctuations in grade, but what's the scale of that heterogeneity? For instance, you might have 100 rocks on a table, and you pick them up and you say, well, this one's got lots of copper, this one has no copper in it. And so you'll see something that goes from 0 grade up to 5% copper. But when I talk about scale, what about when you're talking about cubic meters or tens of cubic meters? And how do you characterize that? Okay? Because that scale is going to be important to trying to assess the potential for a bulk sorting system. And this is an area why collaborating with groups like MDRU are important, because you understand the geology in a much greater level of detail than I would as a mineral process engineer. The second thing is sensor evaluation. So there's a whole lot of sensors that are being developed, and a lot of them are being developed for sensor-based sorting of rocks. Can they detect the heterogeneity? If they can't detect the differences in the material, then you can't apply a technology to take advantage of that. If you find a sensor that can distinguish between what's waste and what's core, then you can go on to say, well, what kind of system are we going to put that into? The most common types of sorting systems, sensor-based sorting systems we have now, are called particle sorters. They were largely developed because of the recycling industry in Europe, where they had to recycle lots of materials, plastics from aluminum. And so they developed these platforms with conveyor belts where individual particles will flow across the conveyor, and a sensor will detect each particle and decide whether it's to be ejected or to be accepted. And so there's some mechanism for actuating like an air nozzle to eject a component and accept a component. And those technologies evolved a lot, but they're limited to about maybe 150 to 200 tons per hour capacity. So they don't meet the needs, or they meet the needs of perhaps some mining operations, but not for large copper mines. But then I talk about bulk sorting. So what does that mean? So that means, can you put a sensor in a shovel and predict the grade of the material in the shovel so that you can decide, does this go to the concentrator or does it go to the waste dump? So now you have a volume of material. Or similarly, for a stretch of material along a conveyor belt, you might have 100 meters of ore and then 200 meters of waste with a diverter system at the end of the conveyor. Okay? So what is that system? And once you know what that system is, you have to be able to assess, well, what does this mean for my deposits? How much of the material, if I'm mining it, I'm going to be able to reject and accept? And then you can apply an economic model to try to assess the potential for sorting. So the first component of that approach was heterogeneity. And we know that we put lots of drill holes in the ground, and from those drill holes we develop block models, and we can assign grades to individual blocks within a deposit, and that informs the mine plan. So that when we're drilling and blasting, we say, well, this block is waste, or this block is ore, and they know that this block of material can go to the concentrator or not. After we drill and blast, we then crush it and grind it to create heterogeneity by liberating the valuable minerals like chalcopyrite so that we could recover them in a process like flotation. Okay, so, but we generally don't pay much attention to heterogeneity between those two endpoints. We know there's significant heterogeneity here. We know we've created heterogeneity here, but this is where we want to try to apply some type of sorting system. There are a lot of sensors that people have been developing that have been developed for other fields that we are trying to apply to rocks. And this is just a few that have been actually applied and tested for bulk sorting. So we have prompt gamma well, there's gamma radiation, which is maybe the first bulk sorting system that has been around since some of the uranium mines in the late 1950s in Canada. But then Stefan mentioned prompt gamma neutron activation analysis. I'm going to show you that. There's X-ray fluorescence, there's electromagnetic. This is just a small sampling of the potential number of sensors that are out there. So I'm going to show you some systems, just to show that the technologies are actually there, and they're being tested and developed and used to some extent. So this is a case where MineSense Technologies, they mounted X-ray fluorescence sensors on a shovel, and as they collect the material, they scan it, and that data goes through an algorithm that converts the spectral data into an estimated grade for the material in the shovel. And so they've gone from pilot scale, like this, to full scale, where you can see 3 XRF sensors on a large shovel. I'm going to show you how well these work later. Then if you want to put it onto a conveyor belt, this is the prompt gamma neutron activation analysis. It's quite clean. It just sits over a conveyor belt, and as the material flows, it's scanning and it's predicting a grade of material, such that the material at the head pulley of the conveyor, so it's being sensed here, could pass through a system like this, where a portion of the stream can be diverted as rejects, depending on the value of the sensor. And this shows an example of an X-ray fluorescence sensor being used to distinguish between saprolite and laterite material, which for nickel deposits, which is important because you have to process these materials differently to recover the nickel. So Stefan said, where do you put this? Well, you can put these systems in different places. So for example, you can have from underground in a block cave operation, material goes through a crusher, you can put the sensors on the conveyor belt that's transporting to surface, and then some means of diverting waste material. So this is critically important for block caves because, or not critically important, but it certainly adds value to block caves because for a block cave, the infrastructure is all developed before you start even mining the material. And then after spending $1 billion or more on developing the mine, you turn on the taps and you start drawing material. And the infrastructure is meant to hold usually one stream. And so you have, and the priority is to control the fragmentation and the evolution of that cave, as was pointed out in some of the previous presentations. The second priority is fragmentation, to try to take advantage of fragmentation, but that's just to make sure that this whole thing is functioning properly. But what means do you have to do any form of grade control? In general, everything will go to the process plant. They can't selectively take from certain parts of the cave and send it to the waste dump because they might start affecting the propagation of the cave itself. So they can do things, but cautiously. So this applies a means of grade control. So heterogeneity, there are different ways of trying to classify that. And we know that when we take the drill core data and we use it and we apply geostatistical methods, we lose information about heterogeneity that we want to try to exploit. So there are a couple of approaches that have been developed. These constitution and distribution heterogeneity numbers, all they are is a variance that shows variation. In the case of constitution heterogeneity, it's variation between rock grades. And in the case of distribution heterogeneity, it's in terms of volumes of material. So we can plot heterogeneity. We can look at a histogram of grade versus weight percent, and we can get a mode and a median and a mean. And based on the shape of this distribution curve, we might be able to say how easy or difficult is it going to be to sort this material. So for instance, if we were trying to sort right here at this grade, because everything below that was waste and everything above it was product, there's a lot of room for error with a small, when trying to distinguish between grades in a narrow size range. If you have a bimodal distribution, well then you know what's ore is ore and what's waste is waste. So then we start to say, well, where do you start? And this is, I think, where ICAR needs to work with the geologists. You start with perhaps the drill core, because that's the first material that you have to work with from a deposit. And you could look at heterogeneity at a small scale. You can see banding of mineralization. And so you would say, well, if you break this up into 5 centimeter pieces, you'd have a lot of 5 centimeter pieces without any metal in it. And maybe you could use a particle sorting system to reject them. But when you start to look at a larger scale, like this is a draw point here from a block cave operation, can you see heterogeneity at that scale? So with drill core, you can see it sometimes quite clearly, but how can you project heterogeneity from drill core for bulk sorting? So in general, when I talk about heterogeneity, when you have larger volumes or larger quantities of material, the heterogeneity is going to be lower. And as you break up into smaller and smaller lots, and smaller, and eventually down to particle sizes or rock size, and eventually into particle sizes that you use for a process like flotation, you'll see that the heterogeneity will increase. So this is those DH and CH values. So for a mineral deposit, you might have different relationships for one deposit than another deposit. Understanding that in the case here, the green deposit may have limited heterogeneity, and there may not be a big opportunity for sorting, whereas the red line represents a greater level of heterogeneity, even at the very large unit size. So one way to look at this is to look at the drill core. And so what this represents here is each line represents a different drill hole. And what we did here, so this drill core was assayed at 3-meter intervals. So let's say you had a 300-meter section of 3-meter intervals. That means you have 100 sections with a copper grade. And now if you put this into an Excel spreadsheet and you reordered it such that you had the highest grade and an associated mass or unit length, and then the second highest grade, you could measure the cumulative metal distribution versus mass or unit length of that drill core. Okay, so this graph is a useful way of looking at the data. So what that says that if you accumulate the 40% of the total drill length that had the highest grades, you would have 90% of all the copper, and that would be 40% of the entire mass, which means that 60% of the mass would have relatively small amounts of copper and is potentially rejectable. So this is at the 3-meter scale. So what does 3 meters represent? I don't know if it represents 30 tons or 40 tons, but it represents a volume of material that's associated with bulk sorting. And so then if you said, okay, well, you can do that, and you can see that for the 5 different drill holes shown here, one of those drill holes showed quite a lot of potential because you get a lot of the metal in a relatively small amount of the mass. But then this brown one here, it shows that 40% of the mass, you get maybe 70% of the metal, which is still not bad. Okay? And you could also predict what would be the grade, the theoretical grade. So this is theoretical projections of what sorting could do based on the drill core at the 3-meter scale. And then if you want to understand, well, how does heterogeneity change with scale? Say, well, okay, now let's take that 300 meters of drill core length with 3-meter intervals, and let's combine every 2 sampled sections, so creating 6-meter sections. And you could follow the same exercise now for 6-meter sections in order to show what these relationships look like and calculate these distribution heterogeneity values. And so as you go from 3 meters to 6 meters to 9 meters, etc., you can see how the heterogeneity decays and decreases. So that's one of the questions that I'm being asked by different mining companies is, how do we assess potential for bulk sorting based on drill core data? So these are the approaches that we've been developing, but I think we're still at early stages and we need better methods of doing this. So now in the context of cave to mill, you've seen information about the New Afton operation, and you know that we've been doing work there. So one of the fortunate things is that for every draw point, they take a sample about every 400 tons and they assay it. So at the 400-ton scale, they have a copper grade. And so we were able to look at that data. And so for a single draw point, which potentially represents a column of material above that draw point, we could look at the histogram of the grades at the 400-ton scale. And you can see here that if you consider the bottom 2 here, which is like below 0.1 or below 0.2, if you combine them, you can see that at the 400-ton scale, almost 25% of the material has no copper in it, or very little copper in it. So that's at the 400-ton scale. So that's important because when you're trying to decide which bulk sorting system you want to apply, you can say, well, we can sort this material at the 400-ton scale. What's a suitable system for that? And from that, we could also develop this same metal distribution versus mass relationship to show how much heterogeneity there is, such that, for example, at 50% of the mass, you get about 90% of the copper, showing that you could reject 50% of that mass and you still get almost all the copper at the 400-ton scale. And then we were allowed to look at all of their draw points, and we got an array of lines that looks like this band here, where you can see that some draw points had a high degree of heterogeneity, represented by the outer lines here, and others had a low degree of heterogeneity. And this could be explained by the location of the draw point. Is it close to the perimeter of the deposit where the mineralized zone is in contact with the host rock? So this informs you to say, well, but in other parts of the deposit, there was very low heterogeneity. So maybe you don't need a bulk sorting system for the center of the deposit, but where you're mining the lower grade materials, or drawing the lower grade materials, you may want to have some type of sorting system for that material. And so for all of those lines, we calculated this DH value, and you can see that the higher the value, the higher the heterogeneity. And we also observed that this distribution heterogeneity, as you increase the grade, it decreases. So again, lower grade material, higher degree of heterogeneity, greater opportunity for sorting. So this is the type of question that some of the mining people that I'm speaking to from mining companies are saying they're trying to quantify this because they need to understand the potential. And then you can map it out for your deposit, and you can say, so this is the west cave, the east cave, and you can see certain areas of the deposit have high degrees of heterogeneity. And so what we did, Stefan directed a program where he took samples from the mine of different grades, and we sent them out for prompt gamma neutron activation analysis. And you can see here that the ICP copper grades for those samples versus the PGNAA predicted grades were pretty accurately predicted. And in addition, he showed you the 200 rocks that he had collected, and he scanned them with a X-ray fluorescence. So this is a surface scanner, and was able to correlate the grades to the bulk grade. So after you scan the surface, then you pulverize the rock and you assay for copper. And he was able to demonstrate this metal recovery versus mass yield relationship for what was theoretical and what the XRF sensor could potentially do. Okay, so you can see that there's an opportunity for particle sorting here as well. And from that, he developed a conceptual flow sheet that looked like this. Here's the cave going to the primary crusher. After crushing, the material drops onto a conveyor belt with a PGNAA sensor that could potentially divide the material into three classes: waste to go to a waste dump, high grade to go to the processing plant, and a smaller intermediate grade material that could then go through a particle sorting system. So in this case, you need a crushing circuit, the screens, individual size fractions are going through a particle sorting system such that you could reject some more waste and produce a high grade product that goes to the process plant. So that was developed as a concept. Afton have installed this PGNAA, and I know that they're working through trying to get it to work for them. But from that, here's a simple mass balance that was produced. The bulk sorting high grade stream had 67% of the mass and 92% of the copper. The particle sorting concentrate had 4% of the mass and 4.6% of the copper. So when you add these two together, you can see you have 97% of the copper, and the other in about 70% of the mass. So you're rejecting 30% of the mass, but it depends what you do with the fines here. The fine material, in this case, has a pretty low content of copper, interesting, because often fines will be enriched. So you have to decide whether or not you want to send that to the process plant or the waste dump. So I just want to quickly show you the shuttle sensing system, because this is now being used at open pit mines, but it's being developed for underground mines like block caves. So we give the operator of a block cave the opportunity to make decisions about the grade at the draw point. And so in this case, the shovel collects the material, and as it's being collected, it scans it with the XRF sensors. So we did I was involved with analysis of the data from a pilot study where a mine generated 10 piles of low-grade material. The shovel picked up the material, scanned it, and then the shovel was brought over to a sample preparation area where the material could be crushed, split for assay. So we had an assay grade and an XRF sensor response. We were then able to correlate the XRF sensor to the assay grade using a multivariable regression model, and then use that model to predict the grade with the XRF sensor system. And so this shows the results. So this was done by an undergraduate student, so I'm sure it's not bad. The R-squared value is 0.85, but you can see the assay copper grade versus the predicted grade. Important to note is that this is 0.05, 0.1, 0.15. So in other words, that shovel sensing system was predicting within plus or minus 0.05%. Okay. So that was, I think, for me, impressive. And for 10 different piles of 10 different grades, the average assay grades versus the predicted grades followed quite closely. And then it's been scaled up. It's been used in large shovels, and this shows some information that it shows the shovel sense average grade, which is the solid line, and the recorded mine grade, and you can see that the shovel sensing system for 75-ton shovels is doing a pretty good job at monitoring the grade. So this is, I think, quite interesting, because when you can do this, what does it mean to the way you plan a mine and operate a mine? What does a cutoff grade mean when you know that a shovel can distinguish between ore and waste with this level of accuracy? And so I've been told that this system is predicting at the 75-ton scale the copper grade within 10%. So the mine that's using this, that when they first, for 6 months, they just tested it and tried to monitor the predicted grade versus what they actually thought the grade was. And after some period of time, when they were in waste material and the shovel system says this is actually above the cutoff, they would send it to the concentrator. And then after a few months of gaining confidence in recovering ore from waste, when they were in ore and the shovel sensing system said this is waste, they were actually diverting waste from ore. So they developed confidence in this technology. And then when you start to say, well, what is the value of that? I mean, that was an open pit mine, and this is an open pit case study, but I think it's equivalent to think about block caving and the opportunity here. A study done by Whittle Consulting showed that compared to the block scale, sorting at the shovel scale increased the NPV by 79% for this mine. So it's a big financial impact. So there are a number of benefits from these sorting systems. It allows you to perhaps expand the footprint of the mine and utilize the resource more fully. To perhaps, because it delinks the mine grade from the grade going to the process plant, so you can perhaps lower the cutoff grade. There are a number of metallurgical benefits. Anything that you do reject, you don't put through your comminution circuit. You don't put a lot of energy into. You don't put a lot of costs into. The feed to the process plant. My belief is that it's going to be more consistent in grade, so the process plant is going to be happier. They're going to be able to operate it with a more consistent feed. And there are a number of environmental implications as well. For example, directly related to water consumption. If you're rejecting 30% of the rock, that's 30% of the rock that does not have to be ground fine in water that ends up in your tailings pond. So, okay. So We know that copper demand is going to increase in the future. We know that innovations are needed to allow us to mine large tonnage, low-grade deposits at depth. Bulk sorting is a relatively new tool that we have that's going to help us to mine those deposits. There is significant potential benefit in terms of profitability and productivity. We are developing these frameworks for how to assess sorting for a deposit. So far, I think that I'm one of the co-founders of a company called MindSense. To see them evolve and get to the point where they are now, I'm curious to see what it's going to do for the mining industry, for either deep underground mines like requiring block caving or surface mines.